Welcome to Lecture 4.2, Symmetric and Hermitian matrices. One of the major themes of this course is uncovering the mathematical structure, usually linear algebra, behind the scenes of the applied mathematics that we're studying. We've done that before regarding differential equations and Fourier series, and we're going to continue that here. We're going to look at symmetric and Hermitian matrices, which represent a certain type of linear maps, and we're going to see what properties those linear maps have. And we will use that as an analogy to generalize this theory to infinite dimensional vector spaces of functions where the linear maps are differential operators. And that's going to be one of the main ideas when we study Sturm-Liouville theory. Okay, so let's get started. Recall the following concept from linear algebra. Let A be an n by n matrix and V a length n vector. If AV equals lambda V for some constant lambda, then we say that V is an eigenvector with eigenvalue lambda. Recall that if you have a 2 by 2 matrix A, then the eigenvalues, let's call them lambda 1 and lambda 2, these are the roots of a degree 2 polynomial. And we'll review this when we see some examples. But in general, there are three cases to consider. Case 1, there are distinct real roots. So let's say without loss of generality that lambda 1 is less than lambda 2. Case 2, there are complex roots. Let's call them a plus bi. And case 3, there are repeated roots. Lambda 1 equals lambda 2. So that happens when this b is equal to 0, and so these things, if they're repeated, they have to be real. Here is a theorem that you might not have seen, even if you've taken a whole semester of linear algebra, and it's important. If a real-valued matrix A is symmetric, that means it is square and its transpose is equal to itself. Remember, that just means that the ij entry equals the aji entry. Equivalently, if you take the matrix and you reflect it across the main diagonal, then each A in this entry has to be equal to that entry. So one of these is the ith row and jth column, and the other one is vice versa. Okay, so if you have a symmetric matrix, then two important things hold. First of all of its eigenvalues are real. So you never have complex eigenvalues, which seems surprising because what does this symmetry have to do with having real eigenvalues? We'll see that in the next lecture. Second property, there is a full orthonormal set or a basis of eigenvectors. So this says two things. It says that you, first of all, have a full set of eigenvectors. You've likely seen examples of when you have deficient, if you have a repeated eigenvalue, you might not have a full set of eigenvectors. So this is saying that doesn't happen. But it's also saying that you can pick the eigenvectors to be orthogonal. And once you have orthogonal eigenvectors, you can always scale them down to be orthonormal. Okay, so we're not going to prove this in this lecture. And in fact, this second part is beyond the scope of this class. It's hard. But what we will do in the next lecture is we will generalize the notion of a symmetric matrix to what's called a self-adjoint mapping. And this will not just hold for matrices, but for things like differential operators. And we will prove that anytime we have a self-adjoint map, then all of the eigenvalues are real. And we can prove a modified version of this eigenvector statement is that eigenvectors for distinct eigenvalues are orthogonal. And that will in many cases imply this result. But once again, this is a little bit beyond the scope of the class. Think of it like when we studied Fourier series. I said that the set of all sines and cosines form an orthonormal basis. It wasn't hard to show that they were orthonormal. It was very hard, and we didn't actually do it, to show that they actually form a basis. That's very technical. Okay, so let's just do some examples. Example 1. Compute the eigenvalues and eigenvectors of this matrix here. 1, 2, 2, 1. Okay, so I'm going to do this quickly because it's something that I expect you've seen before, and I just want to get the answers. So remember that to compute the eigenvectors, you need to compute the determinant of a minus lambda I and set that equal to 0. So if we do that, the determinant of a minus lambda I is 1 minus lambda, 2, 2, 1 minus lambda. And so this is 1 minus lambda squared minus 4. So this is lambda squared minus 2 lambda plus 1 minus 4. This is lambda squared minus 2 lambda minus 3, and this is lambda minus 1, lambda minus 3. One of these is going to be negative or positive. This is 0. So we get lambda 1 equals negative 1, and lambda 2 equals 3. Okay, so here are our eigenvectors. So now our eigenvalues. Now how do you find the eigenvectors? Well, if the determinant of a minus lambda I is 0, that means this is non-invertible, which means there is a vector in the null space that's non-trivial. So we have to find that. So lambda 1 equals negative 1. What we do is we take a minus lambda I, and we get negative 2. Oh, how about if I just write that out, just to remind you. A minus negative 1 I times x equals 0, or v equals 0. So this is a minus negative 1 I, so this is negative 2, 2, 2, oh, positive 2, 2, times, say, x1, x2 equals 0, 0. So this is a system of equations 2x1 plus 2x2 equals 0. We can divide through by 2, and we get, and again, the other, as always is the case, these two things are going to be the same. 2x1 plus 2x2 equals 0, so we can get rid of one of them, and this just tells us that x1 equals negative x2. So that means that our eigenvector, let me call it, instead of x, let me call it v1. So v1 equals, well, whatever x1 is, x2 is the opposite. So 1, negative 1, or negative 1, 1. So that's v1, and now let's do lambda 2 equals 3. Now if you believe this theorem, and you want to plot these eigenvectors, and I've already told you that one of them is 1, negative 1, well, that's this line here. And if you believe that the eigenvectors are orthogonal, or orthonormal, that means that the other one, there's only one possibility because we're in 2 dimensions. It has to be that one. So let's check to see that this actually is the case. Okay, so a minus 3I times x equals 0. So this is negative 2, 2, 2, negative 2. x1, x2 equals 0, 0. We get the same thing, but now we have negative 2x1 plus 2x2 equals 0. I don't even need to write the other one. And that means that x1 equals x2. So v2 equals 1, 1. Okay, so here are our 2 eigenvectors. Now, 2 comments. First of all, these are not orthonormal because they're not unit length. I'm not saying that any full set of eigenvectors are orthonormal, because you can always scale up, but I'm saying we can find, there is one, a full set, a orthonormal basis of eigenvectors. So in other words, if we go up here to this picture, so if I pick these 2 vectors, let me call this one root 2 over 2 and root 2 over 2. Now one of these is going to make that negative, or if you want to make the other one negative, it goes down there, it doesn't matter. And then this one here is root 2 over 2, root 2 over 2. So here is our full set. Here is our basis. This is a basis for R2. This is a basis of eigenvectors, and this is an orthonormal set. Okay, so we found them. Last comment is just because this is a little more subtle, it just says there is a full set of eigenvectors. So what if I give you the matrix A equals I, the identity matrix? Everything is an eigenvector because IV equals 1 times V. So if you look at R2, you can certainly find a basis for R2 of eigenvectors which are not orthonormal or even orthogonal. This works. Take E1 and then take whatever this root 2, take 1, 1. This one. This is a basis for R2. This is an eigenvector for I because every vector is an eigenvector, but it's not an orthonormal or even orthogonal set. That's not a problem. This is not saying that every full set of eigenvectors or basis of eigenvectors is orthonormal. It just says there is one. Because what you could do instead is you could just say, hey, let's just take E1 and let's just take E2, and that is a basis of eigenvectors. And this theorem just says we can always do this. It always helps to do non-examples with examples. So here are two non-symmetric matrices. Let's consider this first one, 3, -9, 4, -3. And let's compute the determinant of b minus lambda I. So that's 3 minus lambda, -9, 4, -3 minus lambda. Now we get 3 minus lambda, -3 minus lambda, plus 36. This is a difference of squares, so we get lambda squared minus 9 plus 36. This is lambda squared plus 27 equals 0. So it's pretty clear here that the eigenvalues are not going to be real. So lambda 1, lambda 2 equals plus or minus square root of 27i. Okay, I'm not going to continue with that because I just wanted to show you that here's an example where the eigenvalues are not real. Here's another example. This is a non-symmetric matrix C, 1, 1, 0, 1. And let's compute the eigenvalues of this and eigenvectors. So the determinant of A minus lambda I, this is 1 minus lambda squared minus 0 equals 0. So that's lambda minus 1 squared equals 0. So lambda equals 1. So sometimes we say lambda 1 equals lambda 2 equals 1. So there's a repeated eigenvalue. Now sometimes when you have repeated eigenvalues, you have multiple eigenvectors. And by that I mean not up to scalar multiple, but two linearly independent eigenvectors. Like if the identity matrix is one of those. For the identity matrix, lambda 1 equals lambda 2, and you can certainly find any two vectors or eigenvectors. So pick E1 and pick E2, and again, there is a basis of eigenvectors that happens to be orthonormal. This, as you will see, is not going to work that way. So let's do C minus lambda I, which is C minus I times x equals 0 to compute the eigenvector. So C minus I is 0, 1, 0, 0 times x1, x2 equals 0, 0. And this first equation says that 0x1 plus x2 equals 0. So that tells us that x2 equals 0. And the first equation, not the first equation, the second equation says that 0x1 plus 0x2 equals 0. That doesn't tell us anything. X1 and any x1 and x2 satisfy that. So this is the only restriction that we have. X2 is 0, and that means that x1 can be anything. So we only have one eigenvector, let's call it v1. X2 is 0, and x1 is anything. Since we always do this up to scalar multiples, we can put a 1 right there. And that is our only eigenvector. So now we don't have a full set of eigenvectors. So a basis of eigenvectors, we would need two of them, and we only have one. So two examples of non-symmetric matrices, and both of these are examples of how one of these conditions will fail. Up until now, we've assumed that all of our matrices are real valued, but now I want to relax this assumption. So suppose that A is a complex valued matrix, and I want to ask what condition on A implies that it will have real eigenvalues and an orthonormal set of eigenvectors. In other words, what's the analog of being symmetric when you have complex valued matrices? The answer is that it has to be Hermitian, which means that A transpose equals not A, but the conjugate of A. So remember that symmetric meant that A transpose equaled A. So an example of this, here's the following. Let's just make up a matrix. 2, 3 plus 5i, 3 minus 5i, and negative 50. This is a Hermitian matrix because if you compare each Aij entry, it's equal to the complex conjugate of each Aj entry. So this entry is not equal to that one, 3 plus 5i, but its conjugate but it's equal to the conjugate of that one. And notice that a corollary of this is that the elements in the diagonal have to be real valued, because this says that AII equals AII transpose, and that can only be the case if AII is real. So this is an example of a Hermitian matrix, though it's not symmetric. And an example of a non-Hermitian but symmetric matrix is the following: 2, 3 plus 5i, 3 plus 5i, and negative 50. So this one is guaranteed to have real eigenvalues in an orthonormal set of eigenvectors. This one is not. It may, by accident, have either of these two properties, but it's no longer a guarantee. Let's do a quick example. So compute the eigenvalues and eigenvectors of this matrix: 0, negative I, and 0. So this is Hermitian. So if we compute determinant of A minus lambda I, we get negative lambda, negative I, and negative lambda. So this is lambda squared minus I squared, and I squared is negative 1. So let's be careful. Minus, there's so many negative ones floating around here. I times negative I. So what is that? So that becomes plus plus, and so that is lambda minus, or plus I squared, which is lambda squared minus 1. That's lambda plus 1 and lambda minus 1. So yes, the eigenvalues here are real. And why are the eigenvectors orthonormal? Or why can we find a full set of orthonormal eigenvectors? Let's check. Well, let's say lambda 1 is equal to 1. And then let's compute A minus lambda I times x equals 0. And if we do that, we get, so let's take this matrix and plug in 1 into this. So we get negative 1, negative I, and negative 1 times x1 and x2, and this is equal to 0, 0. So if we do this, we get negative x1 minus I x2 equals 0. And so we get that x1 equals, be careful, x1 equals negative I times x2. So that means that whatever the heck x2 is, let's call that 1. So if the x2 entry is 1, then the x1 entry is negative I times 1. So 1 and negative I goes here. So this is, let's say that v1, and then v2 is when lambda 2 equals negative 1. So now A minus lambda I times x equals 0, and by 0 I mean the 0 vector. That is if that's 1 negative I 1 times x1 x2 equals 0, 0. And now we get x1 minus I x2 equals 0. And by the way, the second equation here is I x1 plus x2 equals 0. It may not look like these things are multiples of each other, but I claim they are. Particularly if you take this equation and multiply it by I, you get that equation. Okay, so this gives us that v2, well, I should say, this tells us that x1 equals I times x2. So whatever the x2 entry, call it 1, the x1 entry is I times that. So I1. Okay, so we have a set of eigenvectors. Are these orthonormal? What is it? Do you remember how to compute the complex inner product now? Let's see. So v1, v2. Now remember how to do that? That was v2 conjugate transpose times v1. So that's I1 negative I1, and we got to put bars on this. This is an I, that's a 1, so remember that I bar is negative I, so we have negative I, 1, negative I1. And if we do this, we get I squared, which is negative 1, plus 1 equals 0. So this indeed passes the test. These eigenvectors they're orthogonal. They're not orthonormal, but you can normalize them. And if you do that, then they become orthonormal. In other words, just multiply this by 1 over root 2, and 1 over root 2, and there is your orthonormal set of eigenvectors. Let's do a non-example for good measure. So this is a symmetric matrix, but it's not Hermitian because these opposite entries are not complex conjugates of each other. So let's compute the eigenvalues of this. So the determinant of A minus lambda I equals negative lambda I negative lambda, and now we get lambda squared minus I squared, and so this is negative lambda minus negative 1, and this is lambda plus 1 equals 0. So right away we see that the eigenvalues lambda 1, 2 is plus or minus I, and that's going to fail this first condition of having real eigenvalues. Throughout this class, we've seen some fundamental concepts like dot product and vectors being perpendicular, and we've generalized these to vector spaces of functions, things like inner products and orthogonality. So we're going to do that again here. So the idea of a linear map being symmetric or Hermitian is actually a special case of a much more general definition that has some very nice properties. So let's let V be a vector space. And suppose there's an inner product. You can think of this as Rn, and the inner product is the dot product. Or you can think of this as a space of periodic functions, and the inner product is an integral, or something else if you want. So a linear map from a vector space to itself is self-adjoint if the following condition holds. If AV.W is equal to V.AW for all vectors V and W in the space. Let's make several important remarks, because this definition probably looks like it came out of left field, and I really want to connect this abstract notion to the notion of a matrix being symmetric. So the first remark is that using the standard dot product in Rn, a matrix A is self-adjoint if and only if it is symmetric. So let's see why that is. So remember that we defined the dot product V dot W to be W transpose V. Okay, so let's see why self-adjoint and symmetric are the same thing. So let's look at this condition here. AV dot W equals V dot AW. So first of all, AV dot W, let's compute that. Not really compute it, just write it out. That's W transpose AV. Let's compare that to V dot AW. So V dot AW equals AW transpose times V, which is W transpose A transpose V. So when are these two things equal? The answer is precisely when A and A transpose are the same. And so that happens precisely when A is symmetric. So that's why you can think of the concept of being self-adjoint as a generalization of symmetric matrices from Rn to a general vector space. Similarly, using the standard inner product in Cn, a matrix is self-adjoint if and only if it is Hermitian. And this is for a similar reason. Remember that V dot W in a complex space is W transpose, conjugate transpose V. And so here, if we do AV dot W, we get W conjugate transpose AV, and compare that to V dot AW, which is AW conjugate transpose V, which is W conjugate transpose A conjugate transpose V. And so once again, these things are going to be the same for all V and W if and only if A and A transpose are equal. Now I want to finish this lecture with one more thing. So I've always said using the standard dot product in Rn, and I haven't really given you an alternative for an inner product in Rn. I have in things like polynomials or periodic functions or things like that, but let's do a simple non-standard dot product in Rn just so I can show you why this is not the only one. So let's define, we can do this in Rn or Cn, but Rn is easier. So let's define v dot w to be w transpose mv, where m is the following matrix. M is 1, 2, 2, 1. Now notice that the standard inner product, v dot w, I write it like this, is w transpose times the identity times v. So think of this as, instead of putting the identity in here, this matrix M is something a little more complicated. So let's actually try to explore this. Spend a few minutes exploring this so we can understand what's going on. So v dot w is w transpose. So I'm going to write that as w1, w2. Now 1, 2, 2, 1 times v1, v2. So this is w1, w2. Let's multiply this out. We get v1 plus 2 v2 and 2v1 plus v2. And this is v1 w1 plus 2 v1 w1 plus, v1 w2 plus v2 w1 plus v2 w2. Okay, so this is a cute way to define a dot product or an inner product. So the standard inner product is just this entry and that entry, but now we have this special little thing in the middle. So just for fun, let's try to explore this and see what is orthogonal to the vector e1 with respect to this inner product. Let's see. So let me write that down. What is orthogonal to e1? Let me remind you what e1 is. That's 1, 0. So let's do that. Let's say that e1 dot w, let's write this out. So let's take this formula and let's plug in, let's take this formula and let's plug in v1 equals 1 and v2 equals 0 and see what happens. So if we do that, well, what goes away? These last two terms go away. Sorry about that. So we get v1 w1 plus 2 v1 w2, and of course v1 is 1, so this is really w1 plus 2 w2, and for this to be orthogonal, this has to be 0. So if we set this equal to 0, then we get w1 equals negative 2 w2. And so that means that any vector w of the form, of what form? So the w1 entry has to be negative 2 times the w2 entry. So whatever w2 is, let's make this 1, w1 has to be negative 2 times it. So where is in this graph here, negative 2, 1, that is this, that's this line here. So it's saying that this line, so that line of slope negative 1/2 is perpendicular to the x-axis. So you might say, well, that's not perpendicular. Well, everything in your mind of being perpendicular is with respect to the standard dot product. This dot product that I've defined is just as good as any other dot product. It's sort of like how base 10 is just as good as base 2 or base 7 or base 16. We're so ingrained and so used to base 10 that when we go to base 8 or something, it seems different, it seems wrong, but there's nothing inherently better about one base than the other, just like there's nothing inherently better about one inner product than another inner product. Let me actually conclude, not quite conclude, but just show you another inner product. So you can replace this matrix I or this matrix M with any symmetric matrix that has only positive eigenvalues, said to be positive definite. But here's another choice. So let's define W dot V equals W transpose times 0, 1, 1, 0 V. So if you do this, then W dot V, sorry, V dot W is, let me write, V1, V2 dot W1, W2. What you actually end up doing, I'll let you verify if you want, is, well, for the standard dot product, you multiply across V1, V1W1 plus V2W2. Now you actually do this sort of twisted thing where you multiply across, and you end up getting V1W2 plus V2W1. So I encourage you to think about what orthogonality is here. Like in this example, what is orthogonal to E1, or what is orthogonal to 1, 1? So again, this doesn't come up that much. It comes up a lot in sometimes in applied math, like statistics. If you want to change norms, these different inner products have their own meaning. But for now, I think it's helpful to see these two examples of, I like to call them non-standard inner products, just so you know that when I say standard dot, that not everything is the standard dot product or the standard inner product. Okay, so let's conclude with the big theorem of this lecture, why we introduced symmetric and Hermitian matrices in the first place. So we introduced this and we said that this is actually a special case of a more general concept of a linear map being self-adjoint. And now the big theorem says that anytime we have a self-adjoint matrix A, then all eigenvalues are real and eigenvectors corresponding to distinct eigenvalues are orthogonal. And then we can scale them down to be orthonormal. Now, very often a lot more is true, but it's just a lot more complicated when we're into infinite dimensional functional spaces. So I think it's just easier to stick with this weaker statement saying if we have distinct eigenvalues, the corresponding eigenvectors are going to be orthogonal. Now, I want you to think about what this means and what this implies in infinite dimensional vector spaces of functions where differential operators are linear maps. So we're going to leave it there. See you next time.